The second part of this introductory series is going to introduce what to do when you have systems in which your solution is not so easy. So one common type of system we like to encounter in linear algebra is something called a homogeneous system. Now, an example of a homogeneous system would be the following: 2x1 minus x2 minus x3 is equal to 0. Negative x1 plus 2x2 minus x3 is equal to 0. Minus x1 minus x2 plus 2x3 is equal to 0. This would be a homogeneous system because, as you see on the right side, everything here, all zeros on the right hand side. Or in other words, in matrix form, the more compact way of writing this for this system is 2, negative 1, negative 1, 0. So I'll do this like this for now, sorry. 2, negative 1, negative 1, negative 1, 2, negative 1, negative 1, negative 1, 2, times our vector, our solution vector we're trying to find, x1, x2, x3 is equal to 0, 0, 0. Or in the language of linear algebra, this is our a, this is our x, and this is our 0 vector. So our homogeneous systems, in other words, homogeneous systems are of the form ax, our matrix A, vector x we're trying to solve for, equals to 0. So that's what a homogeneous system is. Now, homogeneous systems are different from what we just did. What we just did was a system in which we had a unique solution. We had one and only one set of values for x1, x2, x3. As we'll see for homogeneous systems, this is not always the case. So consider the system here. Let's try and actually solve this equation ax equals 0. So if we take our matrix, let's see, it's a 2, minus 1, minus 1, minus 1, 2, minus 1, minus 1, minus 1, 2. We augment it with zeros, we can try and solve for x1, x2, x3. So let's do just another exercise. Let's perform Gaussian elimination on this again. So let's take r3 times negative 1, and let's then swap, after that, let's swap r1 and r3. So what we do, when we perform this operation, we get the following. It's always going to be zeros on the right side, so you can just write that right away. Because 0 times anything is a 0. So we get this matrix here, 2 minus 1 minus 1. We multiply r3 by negative 1, and then we swap r3 and r1. Now, at this point here, we have formed a pivot in the top left. And pivots are crucial to everything in matrix row reduction. So now we want to create zeros here. So let's do r2 plus r1, and let's do r3 minus 2r1. And this gives us here, so remember we're not operating on r1 here, so r1 has to necessarily stay the same. So r1 stays the same. These are still zeros. And what we're left with is 0, 3, minus 3, 0, minus 3, and 3. So you can confirm this. So r3, 2 minus 2 times r1, that would be a 0. Negative 1 minus 4, negative 1 minus 2 is negative 3. Negative 1 minus 2 times negative 2 is 3. So this is our form here. Now what you see here, this is a nice form here. We can actually just take r3 here and add r2, and that'll completely get rid of our r3. So we're not operating on r1. That stays the same. We are also not operating here on this row operation. We're not operating on row 2. So this stays the same. And now we're going to take this row and we're going to add this row to it. So this becomes a 0 and a 0. So that cleans things up nicely. Now we want to create a leading one here. So let's just do R2 R2 divided by 3, but in terms of row operations, we do R2 times 1 over 3. I know it's the same thing, but we always do it in terms of multiplication. So this stays the same. We're not operating on R3. R1 also stays the same, which is 1, 1, minus 2. And this is just 1, 0, 1, negative 1. Okay? Now let's take here, at this point, let's take R1 and we're going to subtract off R2. So we're nearly there. We're almost in fully reduced form. So we're not operating on R2 still, so it's going to be 0, 1, minus 1, 0, 0, 0, 0, 0, 0. This is still 1. This is going to become a 0, minus 2, minus negative 1 is minus 1. So that's our new form here. And this is actually in fully reduced form. So this is in RREF. You don't have to have a full staircase of ones. You just need to make sure that for every pivot you do have, in that same column, there's only zeros. That's the definition of row reduced echelon form. I will not write out the full definition just to save some time here. Now, once we have row reduced echelon form, we want to actually get the general solution. So we want to solve for x1, x2, and x3. Now we can't just say x1 equals some number, x2 equals some number, because these are non-zeros, right? So it's not like a unique solution. So if we look at what the equations mean here, let's look at the first row. The first row tells us x1 plus 0x2 minus x3 is equal to 0, which is true if and only if x1 is equal to x3. Right, that's just pretty obvious arrangement here. And row 2 tells us 0x1 plus x2, well technically 1x2, but I'm not going to write that, minus x3 equals 0, which is if and only if x2 equals x3. And the last row doesn't tell us anything. It tells us 0 equals 0, which does not introduce any new constraints. But now, okay, so we have these conditions here, but how do we get our general solution? Remember, we want x1, x2, x3, right? So x1, x2, x3, as you'll see here, x1 and x2, they both have leading ones. So what we like to say is x1 and x2 are so-called basic variables because they correspond to pivots in RREF of A. So if there's a pivot in that column, then that variable is a basic variable. Now x3, there is no pivot, and this is fully reduced. So what we like to call for variables that have no pivot, x3 would be is called a free variable. Why is it called a free variable? It's because it can be anything. It can be any scalar. So it's called a free variable, and this is when there is no pivot. Okay? So since x3 is a free variable, let's now call x3 here. It can be anything. So let's say x3 is equal to s. So x3 is equal to some value s, where s is a scalar. S is just a real number. So this is our free variable. S is our free variable, and we're saying x3, which is a free variable, is equal to some scalar s. Now we can express x1, x2 in terms of s because we know x1, x2 in terms of x3. So x1 is equal to x3, so that means x1 equals s, x2 is equal to x3, which means x2 equals s, and x3 is equal to s by definition of x3 here. Now I chose an easy case, so like not to mess up the algebra here, but the concept's always the same. So this tells us our vector x1, x2, x3 is any scalar here. So what's this actually tell us? So if we factor out s here, this tells us x1, x2, x3 is equal to some scalar times the vector 1, 1, 1. So this might be confusing. So if someone tells you what's the solution to this equation, what this means is that your solution x1, x2, x3 is just any number times this vector here. So in other words, if say you pick s equals to 1, that means x1, x2, x3 is equal to 1, 1, 1 is a solution. If you pick, I don't know, I'm just trying to beat for, if you pick s equals to negative 40, you You can pick s equals to any real number that tells you that x1, x2, x3 is equal to negative 40, negative 40, negative 40 is also a solution, right? So it's a free variable, and any value you pick for the free variable will not change the solution. So therefore, there's actually infinitely many solutions to this homogeneous system, and that comes about because this variable is free. It adds a sort of it adds infinite solutions because you can have any value of s. So what this form here, x1, x2, x3 equals s times 1, 1, 1. So x1, x2, x3, the vector or solution vector, equals to s times 1, 1, 1. This is what we call our general solution to ax equals 0. In other words, in this case, our x1, x2, x3, what we've just found is the set of all x vectors, all solution vectors, which belong to the set Rn, such that ax equals 0, which is precisely what we just found. We found all x's such that ax equals 0. That's what the equation we were trying to solve. And now, just to connect this back to what we've learned in first year, this is the null space of A. The null space of A just means the set of all inputs that when you multiply it by your matrix, it equals a 0 vector. So the set of all inputs here is x, and when you multiply it by A, you get the 0 vector. So that is our null space of A. So this is going to form a basis for how we define eigenvalues and eigenvectors in later videos. And this is how you go about solving equations in which there are more than one solution. There's infinitely many solutions. I hope this is helpful.